Final speaker is Jeremy Levitt, Principal Engineer, Questa Formal R&D at Mentor, a Siemens business. It's been 24 hours. Should I kill my formal run? A very intriguing title. Jeremy is a Principal Engineer in the Formal Verification Group of Mentor, a Siemens business. He oversees R&D with a focus on algorithm development. Jeremy earned his PhD in electrical engineering from Stanford in 1997, an MS in 1993, and a BA in engineering science from the University of Toronto in 1991. He's based in Cambridge. Over to you. Thank you, Jeremy.
Okay, thanks, Mike. So as Mike said, I'm on the R&D side at Mentor, working on the Questa Formal tools. And I'm going to talk about something which many of you are probably very familiar with. This is when you've been running for a day or 2 days or 3 days, and your properties are not converging, and you want to know what to do next. What should we do? And within R&D, this is a scenario we encounter very frequently. Either we get test cases from our development partners, to improve our tools and to improve our products, or we get a situation like this, which actually the day I was putting together the slides came in, where a customer has a critical property and they're not getting convergence, and they're saying, what do we do? And we need some help. So R&D spent a lot of time over the years looking into these issues. But before I talk about what to do after your first day of running, let's first of all make sure you get the most out of that first 24 hours. So there's some simple house cleaning issues here. If you have a complex property you want to verify, if you can break that down into simpler properties, that will both probably make, reduce the amount of error in your writing of the SBA properties, and will also make it easier for the tools to get kind of closure on. And also, when you start off, we'll see later, if you want to start off with a fairly simple set of basic assumptions and constraints. As we'll see later, adding too many assumptions can actually degrade performance. The second point here is, in that first 24 hours, you want to get as much CPU analysis as possible. So run multi-core on your grid, make sure you're using lots of compute resources. And if this is a project you've worked on, I've been working on, you've seen engines which are non-default engines, which have worked well in the past, by all means, turn them on. And then lastly here, once you've started your run, don't just come back a day later. You need to monitor it and make sure that the environment's working properly, the compute resources are there, and make sure that you're actually getting what you expect 24 hours later. So check that your cover properties are being hit, check that your sanity checks are being satisfied, and make sure that on your grid you're getting the correct CPU utilization, and your memory consumption is certainly within the grid submit limit that you specified. So the tools, our tools, all tools pretty much provide nice graphs where you can look at, easily monitor the progress. So up here we have on the top left, there's the CPU utilization, so you can see it's all above 96%, so that's good. And then all there you can see the result of the cover properties, the coverage. So you can see there that there's a little bit of orange. So some of the properties are actually uncoverable. So that might be something you want to take a quick look at. And then at the bottom right, we have the sanity checks, or sorry, acuity checks. And there we have a few properties which are being proved as vacuously. They're being vacuously proved. So you again might want to check that and just make sure that your setup's good and there's a good explanation for that. For those of you addicted to the phone, there are also mobile apps, so you can check this, in bed or over dinner. I don't recommend that, but maybe it's better than playing games. So you've done all this, and the situation is 24 hours later, a day later, you still have inconclusive properties. So what do? You keep running and just let it run for another day or 2 more days? Or do you stop the run, kill it, take a look at what's going on, make some adjustments and rerun? The arguments to keep on running are that maybe in the past you've seen results after several days, so this might happen again. Compute resources might not be that expensive, and sometimes people get superstitious and they just want to keep on running. Drawbacks are obviously it could be a complete waste of resources, and just to keep track of all these extra runs, that can that takes some manual effort to keep track of what's going on. On the kill manually investigate and start overside. If you do have a difficult property, that might be the only way to get closure on it. And if you start now, you get closure earlier. And if the original run wasn't going to finish, by killing it now, you free up compute resources. Cons, of course, are that if your original run was going to conclude and then you spent your time manually investing and trying to figure out how to improve it, that time is a little bit wasted, and your time is the most valuable resource. So that wastes your time and can impact schedule. All right, so in order to know what to do, the real question is, why is the tool still running? What is it doing that that it hasn't got closure on these properties yet? Obviously, some of the properties are hard, and there are various reasons for that. The property could have a lot of latency and specification. The design could have a big counter in it, which is forcing a lot of analysis. You could have logic, which is unfriendly for formal, so wide multipliers to feed a bunch of algorithms, other structures which are problematic. The property could involve a lot of design state, and so the amount of state space to explore is just huge. Or it could be some other reason. Whatever it is, the question is, when is this analysis going to complete? And all the tools contain, most of the engines in the tools are complete and sound, meaning that if you ran it for long enough and had sufficient memory, you would get an answer. The problem is that it's not possible to know in advance how long is long enough. I mean, it could be centuries or millennia. So, do you have enough time and memory to wait? And this brings us to the real exercise here, which is this is the triage process. We don't know how long these properties are going to take to converge. So the task here is, and we have a fixed amount of time ourselves to invest in this. So the task here is to identify the properties which are most unlikely to conclude in a reasonable time and focus on them first. So we want to minimize the amount of our time and maximize the amount of work to be done with the CPUs. So in order to understand what's going on, we need to dig a little bit deeper. And we need to see what is each individual engine doing. Why are the engines not making progress? And I sort of draw on this graph here, which is just a rough freehand graph showing how the different engines behave, the likelihood of getting a solve as time progresses. And you can see an engine like K induction, if that doesn't solve it in the first 15 minutes, let's say, you're very unlikely to get a solution from that, no matter how long you run. Whereas an engine like bounded model checking, that is a different sort of characteristic. That can make steady, reasonable progress for hours or days, but at some point it gets to a point where each additional increment in the bound is taking exponentially longer to achieve. And once you reach that point, you're kind of at the point where BMC breaks down, and you're unlikely to get results from that. IC3 is a very nice algorithm. This is very frugal with memory consumption, and so that can run for days or even weeks and make good progress towards getting it approved. And then the last example here is symbolic model checking, BDD based. And so this can happily run for hours, sometimes days, but ultimately breaks down if the abstraction involves too much state. And then the BDDs blow up, and you won't, doesn't matter how much longer you run out of memory. So in order to know how you're doing and whether or not you're likely to get benefit from running longer, you need to look at the characteristics of each engine and figure out how is each engine doing on your property. So within R&D, when we have this sort of challenge presented to us, the first thing the engineers do is they start up the debugger and they attach the process and they try to figure out, for each engine, what is going on. Is the engine stuck, making very slow progress and unlikely to finish, or is it just humming along and, it's continuing to make good progress and keep on running? So for each engine, there's specific parameters to look at. It might be the number of clauses being generated, the rate of clauses being generated, the size of the clause, the types of clauses, the size of the BDDs, the size of the abstraction. Each engine has a bunch of parameters which the engine developer could go and look at to try to estimate, is this engine making good progress, or is it running so slowly through the search space that you're unlikely ever to conclude on this property, at least soon enough, like not in the next couple of months. And after doing this for quite a while, we realized that we could just report this information to the users in the form of called engine health. So we simplified it down to 3 colors because this is somewhat of an art. Again, there's no way to know how long it will actually take. But you can judge at the moment how efficiently it's going through the search space. And so we break it down to 3 colors, red, yellow, and green. And where an engine which is red or unhealthy is much less likely to complete because it's bogged down in some part of the search space. Now, as I said, this is an instantaneous sort of judgment as to whether the engine is doing a good job. So it could be that it's just pushing through a very difficult part of the search space, and once it's through that, it will speed up, and the rate of search space exploration will accelerate again. But we found in practice this isn't typical. Once it gets wedged doing something, it's going to be wedged there for longer than you care to wait. So for the end user, what this means is that if after running for a day, you want to get involved and see if you can manually accelerate things, you want to start on the properties which have which have a health of red, or for which all the engines are stuck, making very slow progress. Okay, so once you've identified the properties you want to focus on, because the engines all seem to be stuck and aren't likely to converge, the next question is to understand, well, why are they stuck? What can I do to change the problem so that the engines can rerun and the engines will make better progress? And so there's several things you can look for. Obviously, if you have 32-bit counters, those can defeat a lot of algorithms. The large arithmetic data paths can defeat a lot of algorithms. Or if a lot of memory, if you have a large memory and each word of that memory is being dragged into the analysis, the amount of state can overwhelm the algorithms. So Questa Formal and our competitors will report the logic which is at the moment being analyzed by each engine. And this is useful because typically the engines will be analyzing a small fraction of the total amount of logic in your design. So it might be 1%, less than 1%, or at most a few percent of all the logic in the design is actually being looked at by the engines. And it's that 1% of the logic where the problem lies. So by focusing on that 1%, you've already made your task a lot easier of identifying what the issue is. And these are ordered by activity, so that the signals at the top of the list are the most active. I'm going to take a slight detour here and point out something important, which is even logic which isn't needed to prove the property, if the engines are busy analyzing it, the engines can get stuck on it, and it will prevent you from getting closure. And I have an example here just to illustrate that. So we have a wire C, and that's a sign, that's a disjunction of checking whether a counter is less than 1 billion here, or whether the function of x, y, and z evaluates true. And the property asserts that when A and B are true, that implies that C must be true. Now the engines might try to solve this by focusing on that counter term, because they realize that if they focus on that term, they can very quickly get a deep bound. And that looks promising. So they have 2 billion term here, and they'll think they're making good progress. Whereas as a designer, you might look at this and realize that, well, the counter can count higher than that, so that's not going to work. And really, you want to focus on this function of x, y, and z. And perhaps when A is asserted, that's always true. So you have the situation where the engines are exploring this counter logic, which is not actually needed to prove the property, but it's going to take them a very long time to figure out that their strategy is not going to work. So even logic which is not needed to prove the property, that will cause the engine to get stuck and prevent you from getting closure in a usable time. So when you're looking at this list of the logic that the engine's analyzing, you want to look carefully and try to identify these structures which are likely to cause problems for the engines. And you can do various filtering, filter by name, filter by type.
Jeremy, you've got 1 minute left, please.
Okay. So if the engine performance is poor, so it was red, and you have logic which looks suspicious to you, the last task here is to identify, what the right action is. So it could be that the logic was brought in order to satisfy an assumption. And we've seen many times that people specify assumptions which are used for one assertion but aren't needed for other assertions. So it could be that to get rid of that logic, you just have to remove that assumption which is not needed to prove this property. So in this case, you turn off the assumption if the logic was brought in by an assumption. It might be the logic actually in the panning cone of the property, like the previous slide, but you know, using your design knowledge, that it's probably not necessary to reason about that logic for the property, in which case you can put a cut point on it and rerun, and that logic will be excluded from analysis. Or very frequently, the logic is both relevant to the proof, and then in that case, you can just somehow simplify the problem. And if you have parameter values you can easily reduce, that's one approach. You can set constraints and restrict the problem. Or, the most powerful, but also the most labor-intensive approach is to abstract the logic. So you capture the essence of what's needed to get the proof, but remove the details which are confusing the engines. So either way, if you have poor engine performance and you can identify suspicious logic, then you have a reason to stop the current run, make the changes, and rerun. So to quickly summarize here, you want to make sure you get as much valuable analysis done in your first 24 hours as possible. So run on the grid, make sure your setup is good. After a day or 2 days or whenever you think you need to get involved, focus on the engines, focus on the properties where all the engines are making poor progress, because those are the ones which are least likely to ever converge the way things are set up. And then for those properties, look at the logic which is being pulled in by the engines and try to identify what constructs could be causing the problems. And then if you can identify problematic logic, then you have a good reason to stop the analysis of that property and make the changes and then restart the analysis again.
Okay, thank you very much, Jeremy. There's no questions online, no questions from Bristol, no questions from Grenoble. Any questions from Cambridge?
Yeah, we have one question here in Cambridge.
Hi. So very early on, you mentioned, adding more constraints or assumptions could actually hinder.
Yeah.
Apart from what you've shown, is there any other way of actually, systematically identifying if your constraints are actually hurting your proofs?
Yeah, so I mean, we see it fairly frequently because usually engineers will just throw in all the assumptions they can think of because they don't want to have to deal with with the problems of false counterexamples and having to weed those out. But this is in our experience the most effective way to weed out the problematic assumptions. You look at the logic being analyzed, and you can filter it down. You can ignore all the logic in the panning cone of the property and just identify logic pulled in purely by assumptions. And then you can narrow that down to which assumptions are pulling in the logic which is problematic. So it's something I don't recommend just throwing in all the assumptions up front, especially if you write them. So you write the minimal set of assumptions and then add additional assumptions as you see you need to rule out counterexamples. And then if you have this problem where you're not converging, at that point, remove individual assumptions for the properties which you're getting stuck on.
Okay, thank you very much, Jeremy.